So we've talked now about the idea of angular velocity and done a couple of examples of angular velocity, one for just the simple rotation of a rigid body about a fixed axis, and the other one we're talking about the motion of a particle, and we've introduced the idea that even a particle can have angular velocity, and that angular velocity depends on what your definition of your coordinate system is. Well, angular acceleration is another quantity which we use a lot when we're talking about rotational motion. It's analogous to linear acceleration, and part of the analogy really has to do with the fact that linear acceleration is defined as the time rate of change of the velocity vector, and angular acceleration is defined as the time rate of change of the angular velocity vector. So from a sort of definitional perspective, it's fairly easy to see how you would do that. If you know what the angular velocity vector is, you can simply take a derivative of it. But let's do a couple of examples of this just to kind of get our brains wrapped around it. So let's first do an example that sort of draws on that turntable example. So here's the turntable. It's a record player. And when we turn on the record player, I'm going to ask the question, what happens? And in particular, what happens to omega, and what happens to alpha. Okay. So, and in order to do that, I actually want to take this record player and sort of turn it sideways so we can kind of look at it sideways. So here is the record player from the side on. Right, there's the turntable. It's sitting on the table. Right, this is the actual turntable that will rotate. So looking from the side on, this thing is going to be rotating like that. From the top down, it will begin to rotate like that. Right? So when I turn it on, let's think about omega, and let's sort of just think about some keyframes for omega. Right? Omega initially is 0. Right? As the record player begins to spin faster and faster, omega gets a little bit bigger, and a little bit bigger, and a little bit bigger, and finally becomes a constant value. And as we figured out when we sort of thought about this before, if this is spinning at 33 revolutions per minute, that's approximately pi radians per second in the k-hat direction, right? Where k-hat is coming out of the page, or in this picture, you know, this is the z direction. Okay. If we think about alpha, right, or the angular acceleration, well, initially, the angular velocity is increasing, and it's increasing in the positive k-hat direction. So I would say my initial value of alpha was positive, and in the k-hat direction, and it stays positive, but gets smaller, and finally becomes 0 once the record player is spun up to its final velocity. So you have this sort of analogy here that's pretty easy to see. I've got the angular velocity going up and becoming constant. During the time the angular velocity is going up, the angular acceleration is constant, or is positive, and then that drops to 0 once the angular velocity has reached a constant value. Okay? So that's a fairly simple example of how we think about angular acceleration. Let's do a slightly more complex example that really emphasizes the vector nature of angular acceleration. So this is an example that you've probably seen this demo before. If not, we'll certainly do this demo in class, just because it's one of those ones that everyone loves because it's so counterintuitively weird. So it's the precession example. So if I imagine having a bicycle wheel, and I set that bicycle wheel spinning, so the wheel, let's say, is spinning like this, coming out of the page, right? So it's spinning like that. And I hang it from my hand using a rope, right? So this is a rope. My hand is up here. That's my hand, really. And I spin it. Right? Well, what's the angular velocity look like? Well, initially, the angular velocity, if I think about this, the wheel is spinning this way. Since it's spinning that way, the angular velocity is going to be to the right, right? So my initial angular velocity vector looks like this, and if I have a coordinate system that has, you know, x going to the right, y going up, and z coming out of the page, right? My initial angular velocity is in the I hat direction, the x direction. Now, if you do this, what happens is the wheel precesses, right? So if you actually watch this, the wheel will not just stay turned in this direction. It will actually gradually turn either clockwise or counterclockwise, and that depends on a lot of stuff, and I'm not even going to try to get that right now. So I may give you the wrong direction as far as the precession goes right now. But the wheel is going to turn. So if I turn this and look at it from the top down, right? So here's the wheel from the top down. It is spinning in this direction, right? My hand is up here holding the wheel on the rope. And I'm going to say that the wheel precesses in this direction. So instead of being pointing this direction, it gradually moves around in that direction. So if you think about what omega is doing, most of the spin is actually around this axis. And so really omega starts out pointing to the right, but then as time goes on, omega starts to point more and more in different directions that basically line up with what the orientation of the wheel is, right? As the wheel precesses a little later, it's like this, and so if I think about how that wheel is spinning, the angular velocity at that point is up like that. By the time the wheel has precessed over to here, it's now spinning, well, anyways, the angular velocity points in that direction, and so on. Well, what does that mean that alpha looks like? Well, the change between this omega and this omega is actually in the if you look at this, you can see the initial change is like that, right? Now I've got this vector changing to this vector. Well, when I think about that, the change is like that. When I think about this vector changing to this vector, the change is like that. So this looks actually a lot like circular motion, right? And in fact, it is circular motion. Omega is changing direction, right, and is going around in a circle. And in order for that velocity to be going around in a circle, the acceleration must be orthogonal to it, and the acceleration also is going around in the circle. So you can sort of see this idea here, this sort of big idea, which of course is directly related to the big idea that acceleration is the time rate of change of linear velocity, is that if I have omega at some time equal t, or t naught, and omega at t naught plus delta t, that the change in that is alpha times delta t, right? So the angular acceleration vector has to be the vector that connects the old angular velocity to the new angular velocity.